Hi everyone, here we are at NXP Tech Days Detroit. Hi, I have Curt next to me. Hi Curt, nice
Hello,
to see
Daniel.
you.
Nice to see you too.
We had 2 fantastic days, a lot of demos, a lot of things, a lot of, it's like, I feel like a kid in a candy shop, an engineer at Tech Days.
We had a lot of customers, a lot of partners. The partners line the whole outside of our demo space here. Yeah.
I wanted to make a little video with you, Curt, and talk about the demo that you have presented these days.
Sure, yeah. I think we'll focus on 2 aspects. One is what we're calling the virtual development environment or the NXP Cloud Studio. So we'll talk about that, but then we're also going to talk about the application that's running in the demo.
Okay.
So why don't I start with the application,
yes,
and then we'll talk about Cloud Studio. So the application uses the NXP model-based design toolbox, and we were able to run a simulated drive around the Michigan M-City test track, and we've archived all of that data, and then we can replay it. So what you see here is something we did actually a couple years ago. We're driving a car around the track, and what we have is the ability to monitor the acceleration, the deceleration, the steering, the GPS locations. Wow. We grab all that data and then we can send that to the cloud. And Amin will talk about that in a few minutes. But the important thing is we take that algorithm and we port that into the S32 Z27, both the physical hardware and the virtual hardware that lives in the cloud. And that's where the Cloud Studio comes in.
Yeah. So basically what you try to do here is to optimize an algorithm.
Yes.
In this particular case, it's a hybrid vehicle, right? So it has a combustion engine, but it also has an electric engine, right?
Electric motor system.
And you want to kind of balance it. So developers for such a solution would have to, balance, look at the algorithm, find the right.
They would do a lot of simulation testing. They would have data from the track. They would have standard drive cycles. The other thing about the chip is it has multiple cores, so you might have one team working on energy management, which is the algorithm that does that torque selection. Another team might be doing battery management, another team electric motor motor control. And so the nice thing about the chip is it has several cores in it. You got to have multiple teams working on multiple applications.
And how this development is done is the problem, right?
That's
that
the problem.
Trying to, ease.
Yes. In the old days, you'd have one ECU with maybe a multi-core device. Maybe it's just 2 cores, and one team can work on that chip. With the mini-core, we've gone from multi-core to mini-core. Then what you have is you have ECUs that are migrating into that one chip. So you have multiple development teams, multiple execution environments or cohorts that have to be integrated. The integration is that gets to be the hard part.
In this example, you go and run in the cloud.
Yes. Yes.
You create a machine, a virtual machine. You would be a developer, right? So you would create a virtual machine. You would get that virtual machine and you would be able to do the development. Let's see how that
Yes. Good questions. So if we look at a very high level picture of what we're doing is we are creating copies of physical assets or physical components. It could be a chip, it could be a battery, it could be a motor, it could be a car. We create a virtual or a digital copy of that, and then we develop on that digital copy. So our digital copy lives in the cloud, okay? And then the nice thing about having it in the cloud is you can provide access to all kinds of developers all around the world, wherever they are. They can be working remote, in the office. You can add 10 developers at a time, 50, 100, 1,000.
So if there is a team of, 100 developers and they all need to work, they can do it because there is a digital twin. Let's use the word,
digital
twin. Because everybody knows digital twin, right? But it's a little, there are subtleties. But let's say there is a digital twin of this car, which resides kind of in the cloud. You can develop your algorithm there, and then you can test it on the board, which in this particular case handles this hybrid vehicle.
Yep, perfect. That's well described.
And then you can test it on the board and see that it works. Let's do this demo. Let's check. Let's
check it out. And let's see if we're telling the truth here. All right. So let me first describe the perspective that we see here. This is an Amazon machine image. Okay, it's a virtual machine and it lives in the Amazon cloud. So this particular instance is being hosted out of Ireland. So when we ran this demo, we are actually talking to the data center in Ireland and it's serving all of this information down to us. Okay. We have the NXP S32 Design Studio over on the left. That's our feature-rich IDE where we have our code and our build process. And then on the right, we have the Synopsys virtualizer. What that is our digital twin. It's a copy of the SoC, the S32 E27 and Z27 in this case, okay? The S32 Z27. And what that is, it's a software copy of the chip. So I can write my software, it runs on the digital copy of the chip, and my software thinks it's running on the real chip. Okay.
All right. So you can do the whole algorithm, development, balancing, everything.
I can make sure it's working. I don't have to have access to hardware. I can have multiple teams working on this. So we're going to go ahead and hit play. This is pre-recorded because of some Wi-Fi issues here in the building. But there I have my algorithm. You can see all of my inputs. This is the call to the HEV optimizing controller. This was done, we took this from a MathWorks pre-built example. So they have a hybrid electric vehicle with an adaptive ECMS, which is equivalent consumption minimization strategy. Say that 5 times fast. And we get our output file here, the S250 RTU basic.elf. That's the file that's going to actually run on the target, either the virtual target or the physical target.
So we have the same file for both targets, the virtual one and the physical one.
Yep, right? Exactly. So this is the Synopsys virtualizer. I have started the simulation. You can see we have a lot of different test configurations here. We can hook up a Canoe for CAN analysis. We have dry stone test. We have a basic software test, and that's the one I'm using.
Okay.
We migrated the algorithm into the basic software project. And then you can do disassembly. You can see all of the registers inside the chip. So if you have a peripheral core, you can see core registers. It really does act like it's
like it'll be a real target, only it's simulated.
Exactly. So our algorithm is going to run, and I think we've hit the initial breakpoint by this time. We're going to go ahead and hit continue up here. And when we do, you're going to see some steps of information come out. You'll see speed, motor torque, and engine torque.
So this is basically the output of the algorithm and values to which we look to see that they are
working.
Correct, right? That
Exactly.
And we expect to see the same values on the target,
yes,
right?
Perfect.
If things work fine.
Yep. That's the $1,000,000 question. We want to make sure that the software we have running in the virtual chip matches the software in the physical chip. That's very important. Yep.
Basically, now we are going on the target, and now we are seeing on the target the same thing.
Yes, let's make sure that we power up our board here. The nice thing about the debugger, it will tell you if it's powered down, so that's good.
It helps, right?
It helps. I did something wrong. And then we're going to fire up here a script. Okay, this is my Detroit Tech Days demo script. Now, the thing about this script, which is interesting, is you remember we used S250 RTU basic.elf. So in the cloud, when I created that file and I tested it, I went ahead and checked that into a Bitbucket repository. And then on my local machine here, I did a pull. Okay, so I had that same file. It's now pulled to my local machine, and we're going to go ahead and we're going to load it. Okay. We've got a status bar down here that we are loading that code into the RAM of the device. And then we will also load the system monitoring unit core, and that brings up the rest of the R52 cores inside the chip, the ARM R52 cores. Okay, we're ready to run. I have something here called MOBA Xterm. Let's make sure it's still running. We have our terminal, and what that means is when we go through those steps, we're going to push the information out the COM port, okay, and that will come in here, and it will be displayed on this display over here on the right, okay? So now we're all set up. We're going to go ahead and hit run. We're going to go, okay? And then let's see our output. Oh, this looks pretty good, right? This looks like the same format, okay? It's working. And now I can look at the data values. I have like a -1 and a 50, a -1 and a 108. And let's go check our cloud-based virtual system. And I can see a -150, a -1 108, a a 0 and a 123.
Some small numbers, but behind it, it's actually a balancing of the torque for the
balancing of the torque to optimize range and then also minimize battery stresses. So these advanced algorithms, they call them multiple input, multiple output. You can have targets and objectives based on anything in your system as long as you have a really good model of how that system's working.
So some small numbers, but some big,
very important.
Big differences in your daily usage of the car, right?
Yep.
All right. Thank you, Curt. Very, very nice. I'll go and talk to Armin afterwards. And
sounds good. Amin's demo has some similar aspects. He has a similar kernel running, but his is a little more broad, and he's going to be pushing data to the cloud.
So basically, he's taking this algorithm and this board, and he's putting it into a car.
Exactly, putting it into a car, having a service-oriented gateway with the S32 G2, and then we push that data up to the AWS cloud, And ICUS also is another partner that has some interesting technology that Amin's going to tell you about.
Yeah.
So.
And one more thing, you know, there is always one more thing. If people want to learn more and they want to see the next use cases and how they can develop with cloud and everything, all they have to do is come to Vegas.
Las Vegas, baby.
So we will be together in Las Vegas at Consumer Electronics early January. So we invite you to join. And,
come by the NXP tent. It's actually a two-story building. It's right off the monorail. And Daniel and I will be there. We will have a more sophisticated demo, and we'll show more about how Cloud Studio can make your life better, speed up your time to market.
Thank you, Curt, very much. It was a pleasure seeing you. Thanks here. And stay close and don't forget to follow up next demos.
Thank you.